This here is the problems class for the week. I hadn't got anything particularly prepared for this. As I said, the problems classes are for you to suggest what you would like to happen. I mean, you can send suggestions through to me by email beforehand or something through on the chat here.
Hi, Philip. I've just got a quick question.
Sure.
It's more so about the assessed homework from Charles.
Yes.
And you know how you've been introducing this new notation.
Yes.
I was just wondering which notation and kind of who will be marking this assessed homework, and which side should we treat it?
I think since there are different kinds of notation, I mean, you can perhaps just choose what you want and just make it clear. Christopher Turner, who marks the weekly homework, will be marking this as well. So, I mean, I think I looked at the assessed homework. I had the impression that actually some of it kind of overlaps with the things we were talking about today. And I think it was just the first question that would have some relevance as to whether you chose different kinds of notation. Let me just look for a moment. Probably turn on the camera. So I'm just trying to find the assessed. Right. Let me try sharing the screen. Just a moment. Looks like I have to download it first. Sorry, it's taking forever. Okay, sorry. So what you can see there. So let's go through. Then I think here for question one, this is the one where there's perhaps the main difference between what he said and what I said. he's got his way of interpreting a term is to think of it as a function on a perhaps unbounded but finite number of variables. So if one's looking at kind of page 8 on his notes, he's looking at interpretations of terms in L structures here. And he thinks of a term as something syntactic, but then he thinks about a collection of variables. So he's going to define a, well, it's I0 to ik minus 1, a k-ary function, right? Now, the k may be more than the number of variables that are free inside the term or are in there inside the term, right? But nevertheless, he's going to define a k-ary function here. So what that just means is that the values of the function on things that are not free variables in the term don't really pay a lot of difference. So, for example, if the term is extremely simple and it's just a constant, then the k-ary function, well, if k is bigger than 0, say, the k-ary function that he's going to define is just going to be the one that returns that constant value all the time. If the term is a function, right? So again, kind of just by an induction on complexity, the k-ary function that he's going to have is, well, the function, but defined to these, using interpretations of these terms that are there within it, right? When k is 0. And then when k is bigger than 0, the k-ary function that's going to be defined, right, is going to be obtained from applying the function f in the structure to the terms here, right? The interpretation of each of the terms within the function here. So by induction hypothesis is that these are also k-ary functions. So altogether, we've got something that's just a k-ary function here. Now, this is a bit more complicated than how I'm defining terms. Right? So I think if you want, I mean, I'm defining, the interpretation of terms as saying, we've got some function here that is actually just taking the natural numbers into the domain.
Philip, sorry, you're slightly above the screen.
Thank you for telling me. Thank you. That happens. So we just look at an assignment of all possible values to free variables. And if the term is something like, a function just of 3 variables like this, we're going to think of the interpretation of the function in the structure as just being what you get by these 3 variables that are here, right? So f, the interpretation of f here on these variables, this is just going to be fm on whatever w0 is, w1 is, and w2 is. Right? Well, if this is 23, this is w23. Right? So I'm defining the interpretation of the function to be just here a 3-place, a ternary function. Right? So when I say we, so me, defines the interpretation of the function. Symbol Fm as a three-ary function. So basically the number of the free variables that's in. So if you look at the cardinality of the collection of the free variables in the function here, it's a function of that kind. Right? So, I mean, I think this is easier, right? I think this is less confusing to just interpret functions to have, you know, the arity that the function itself has. Right? So of course, if we've got a function that's like this, right, maybe this itself is a function of two things. We have V23, right? This is a function with two free variables in, but the free variables in here, in this term, are, you know, there's four of them, V0, V1, V2, V3, right? So here the free variables of this function, let's say this is the term here, the free variables of this term, the size of this is 4, right? There are 4 free variables in here. So the function is originally ternary. It's the term itself is 4-ary, because the term is this function composed with this binary function here. So I think to go back to the question, the question here, I mean, I think you could answer this question using either form of notation if you wanted. I think the question becomes rather simple, actually, if you use my form of interpreting functions. Because in fact, then there would be, well, I don't want to say too much, but I mean, it's, yes, I think it would be easier to use my form of notation. But the question is intended to be done using Charles Morgan's interpretation. But I think if you can't manage it, or you don't understand what's going on in that form, then you could try using my notation there in that question. So now, but then for the other questions, I think it makes little difference, right? What is the question here about? Well, I'm going to set some questions this week, which are also very similar to this, and 2 and 3 actually. So we'll be essentially repeating or going over this bit of material again. So here, the question of what are the free variables of phi, right? In here, it makes little difference actually whether this is an exists or for all. So if you want to answer the question with exists in, actually you're going to end up with the same answers if you put in for alls. So I don't mind whether you change those exists to for alls. You'll be getting the same answer. And question 3 and 4, these are not dependent upon any kind of choice of what the basic auxiliary vocabulary is, or what you mean by interpretation of terms. Right? There's something else altogether. So I don't know, is that answering the question?
Yeah, that's absolutely perfect. Thank you.
Has that said enough?
Yeah, I think there was a question in the chat, actually.
Yeah. Is there a way you could write the question in your notation? Okay, let's go back to it. It's hard to do without giving the whole game away. you see, what the question is asking about, they really are asking for, you know, a k-ary or an n-ary function here for each n, right? Which really only makes sense in Charles Morgan's conception of what an interpretation is going to be. I mean, the point would be, is that if T is a closed term, you know, what does that mean? Well, if you look up what closed term means, it means there are no free variables. Right? So a closed term is one, like a sentence, is something with 0 free variables in it. So basically, it's like a zero-ary function. Right? And okay, he talks about functions being n-ary for any n to interpret terms. So the crucial part of the function only has 0 free variables in it. And the rest of it is just expansion. So actually the answer is it's rather hard to turn that into a question, which is just in my notation. I mean, let me think what one can,
I think Charles might actually say that his definition of a closed term is that it contains no variables at all, rather than the free variables. Yeah.
Right, but remember that in a term, all variables are free. The only way a variable becomes unfree is because there's a quantifier somewhere around in a formula. So I mean, what is a term? I mean, it's something like this. Variable, constant symbol. Or maybe it's a function of 2 variables, like this. Or maybe it's a something like this, right? So here, wherever variables occur, they are not bound, they're free. So the free variables of a term literally just is, you just count up how many variables appear, right? How many different variables appear. In a constant term, there are no free variables, right? So the free variables of D is 0, is the empty set, right? And the free variables of this one is just V1, V5, V3. Right? So the only way, I mean, the only time which a variable becomes unfree is when you've got a formula and you've got something like this. Right? So here we've got an atomic formula relating to terms. So it looks like something is commuting down in here, right? And the free variables in this formula, so now it's a formula, it's not a term. So let's call this psi. So the free variables of psi here are just V0, because the V1 has become bound by this. So yeah, in any term, you just look and see what variables there are, and those are the free variables. Something can only become unfree if it's bound by a quantifier, so in a formula.
Thanks.
Yeah. So trying to work out what to say here about that question. I mean, so the point is that T being a closed term, T means, well, basically it's got no variables in it, right? So a typical closed term is closed term, well, D, constant, right? It's got no free variables in it. F of CD, right? No free variables. F of G of dA, comma E, right? No free variables. So the only closed terms are constants and functions applied to constants, built up like this. Right? So the idea is that, of course, well, there's nothing varying here. Right? This is always D, and this is, well, whatever it is, and this is what it is here. So a closed term should be interpreted as a constant thing. But because Charles wanted to have interpretations where interpretation of a term might be some, any K-ary function. So in this particular case, he wants to define n-ary functions from this. If you look at his definition, what you've got is the n-ary function which interprets D here is just the constant function that gives you the interpretation of D, right? So here for Charles, this is an n-ary function, right? I mean, the interpretation of D here in M as an n-ary function actually it's just D. So dm in here, if you just choose n things, yeah, this is always just going to be D. So I'm using D twice. I mean, it's going to be the interpretation of whatever this constant is here. So that's kind of the base case of the exercise here. When he says use induction on the construction of the term here. So the argument here will be saying, okay, we want an n-ary function. So we look at the n-ary functions we get from here and here, and we compose those and we get an n-ary function overall here. Well, the n-ary functions which we get for C and D always return whatever the interpretation of this constant symbol and this constant symbol are. So then the n-ary function we get overall is just what, well, the interpretation of F is applied to the interpretation of this constant symbol and this constant symbol. So again, it's constant. It's not a terribly important property to have, actually. So, I mean, if it hadn't been set, I would almost be saying, well, let's not bother with this one, right? So is it, so you're asking about this. I mean, is this, are you finding this difficult to understand? Is this the point?
I think that's all understood now.
Can we assume that a function applied to a constant is a constant? Yes, because it's like saying, what about the squaring function? if I apply the squaring function to 3, I get the constant 9. Right? If I apply the multiplication function to the constants 6 and 8, I get 48. So yes, a function applied to constants gives me a constant. So one question come through, saying we covered quite a lot of what we did with Charles in some of these recap lectures that I've done. I was just wondering if in the exam we were required to know what we did with Charles as well as, or just you. I mean, the simple answer is you need to know both, right? What Charles did and what I did. So, because what I'm going to be doing, you can see that some of my definitions are just repetitions of what Charles did, because I'm trying to do a recapitulation. Right? I'm not trying to change too much of what Charles did. And perhaps only this interpretation of these of terms is the only kind of real difference about the basics. The changing of we're going to use or and arrow rather than and not, rather than exists and not, and I think he had and, I don't remember, maybe it was all, but this change is kind of trivial, right? I mean, I can define any of these in terms of these and vice versa. So this is not a big deal, right? But a lot of the definitions that he used, like sort of elementary equivalence and isomorphism between structures and things like this, these are we're all going to use. So these will come back. So yeah, several people have asked me about, they're concerned about the compactness theorem. I'm going to redo the compactness theorem later. So in answer, the question about, do we have to know everything that Charles has done? I mean, it's slightly nuanced. I said yes, in principle. But actually, something like the compactness theorem, I'm going to redo again and talk more about it. So I'm going to cover the compactness theorem once more. And that'll give you a different proof for that, which I think in general people may find more amenable. But yes, you should be familiar with both parts of the notes. I'm trying to kind of merge, or I have an old set of printed notes, trying to merge my notes with what Charles has done, including the numbering of theorems and examples, and trying to get things to fit as much as possible. But in the end, I don't think it's it should be, I think it should be all right. So I will set some more homework. What I'm intending to do is on Wednesdays to set homework for the following Thursday week, a week on Thursday. So I'll send something today. I'll send an email out about that. So of course it's not due tomorrow, Thursday, but a week tomorrow, noon. It'll be set up to be submitted in the usual way over Blackboard. So that's notwithstanding the fact that, in fact, the assessed homework, you've got an extension on the deadline till next Monday, right at noon. So there'll also be something that for Monday, and then there will also be an ordinary homework for the following Thursday next week. But the homework will be from the exercises, the next set of exercises printed in the notes. And if you see, they're all about, well, questions. It's re-asking questions, that some of which are on that assessed homework, about free variables and interpretations in formulae. Okay, so let's just look at that first problem set, unless there's something that's more urgent or something that somebody wants to discuss. Okay. I mean, let's just look at some of these exercises then. I'm probably going to set the last three here on the list. So these are, I mean, the first two are just about some basic mechanics here, just basic nuts and bolts. It just asks you to compute the complexity of these various terms. Right? So, I mean, you just look back and see what the definition of the complexity is, right, here. So a complexity of a variable, I probably said it had complexity 0. Let me just check myself. That's just asking you to look back here at this definition, where I went back and defined what terms and their complexity was. So variables had complexity 0. A constant symbol we give complexity 1 to. It's actually, in a sense, a constant is really a zero function. Right? But let's not worry about that. And then the complexity of a function applied to some terms is the maximum of the complexity of the components plus 1. So each time we're building things up more and more, we add on another layer of complexity. So, you know, I think this exercise is kind of a doddle, really. I mean, you just look at it and just work out what these numbers are going to be here. Right? I mean, this has got complexity 0, there's V2 by itself. A and B have got complexity 1 because they're constants. So this means the complexity of this F here is 2. It's 1 more than the maximum of the components. And you can just go through and do the other things like that. They're kind of straightforward. You know, you just have to look at the innermost thing inside the term. Right? So here we have G. This has got A's got complexity 1, 0, and 0. So this has got complexity 2. And somehow it looks like there's some kind of misprint going on here. There should be a F should be, what should it be? It should be binary. Right? So there should be something in here. I wonder what's missing. I mean, it doesn't matter as long as I count correctly. So G looks like it's ternary. So I want 1, 2, 3. So this is the end of the outer F. So this should be binary. So I just need something in here. So let me just put in here V5. So that goes with this, that goes with this, and now we've got B and T. Right, so there's a misprint with that V5 missing. Okay, complexity 1. 0, 0, so this has got complexity 2. Okay, complexity 2, complexity 0, this has got complexity 3. Right? So complexity 3, complexity 1, T we're told is complexity 4, right? So this, sorry, it's covering up too much. This had complexity 3, complexity 1, so this has complexity 4 here. 1, 2, 3, yeah. This has got complexity 4, complexity 1. This has got complexity 4, we're told. So altogether, the maximum complexities here are 4. Add 1, it's 5. Okay, so it's completely algorithmic. Right? It's quite easy. So something here is asking you to work out the complexities of these formulae. Now this is a little bit subtle, but not a lot, right? We go back and look at how to define complexity of formulae, and it's kind of similar idea, right? We just add 1 each time we put on a negation. We add 1 to the maximum of the two complexities here and here. For the atomic formulae, right, we count them as having complexity 0, right? Even if the terms inside have high complexity. I mean, Tn may have complexity 3 million or something. That doesn't matter. As a formula, it's got complexity 0. And when we add on a universal quantifier, we add 1 to the complexity. Now, this is, I mean, these are not necessarily things that you have to remember, but the idea is that the point is that we can assign numbers, complexity values to terms in formulae, and then that way we can do inductions over formulae. We can say, if all formulae of complexity n have a certain property p, and then you show, okay, if that implies all formulae of complexity n plus 1 have property p, then, you know, hey presto, by induction, you know all formulae have property p. So that's the reason for this kind of number assignment of complexity values to formulae, and ditto for terms here. That's why we do it. Here, there is, you know, you've been left to puzzle out complexities of formulae which don't have, here we just use not an arrow, right? We don't use and by implication and or. We define those in terms of not an arrow. So if you defined, you know, something like, you know, what is the complexity of phi and psi here, or phi or psi here. Well, how do we define phi or psi? This is the same as not phi arrows psi. Okay. So if phi has got complexity 3 and complexity of psi is 4, what we have here is this has now got complexity 4, right? This has got complexity 4. The complexity of the whole thing is now 1 more than these two. So the complexity of phi and psi is 5. Here. So, and then sorry, this is or. So phi and psi, this is equivalent to not phi or not psi. Okay. right? So in general, right? I mean, if this complexity of phi here is k and the complexity of psi is L, then for phi or psi, this has got a value, what is this? This would then be k plus 1. This has got value L, right? So this complexity here is the maximum of these 2 plus 1. K plus 1, or L, that's a 1, plus 1.
Sorry, Philip, could you move the screen down a bit?
Thanks. Okay, so now when you want to work out the complexity of phi and psi, you're going to have to build in, well, it depends on how you want to do it. If you define and in terms of or like this, you're going to have to work out an expression for the complexity of this in terms of k and L, right, here. But it's just a puzzle, right? I mean, it's not, there's nothing conceptually difficult about it. It's just working out what the additions are, right? And again, if we're going to work out what the complexity of this is, suppose the complexity of psi is k, right? Well, we just have to be a little bit careful because we are thinking of this as not for all v2, not psi. Right? So if psi has got complexity k, this has got complexity k plus 1, k plus 2, k plus 3. Right? So complexity of this is k plus 3, whereas the complexity of 4v2 psi, this will just be k plus 1. Okay, so it's slightly funny that exists gets a higher number than this, but it doesn't matter, right? It's only just a way of stratifying our formulae by numbers so that we can do inductions. So the complexity, what the numbers are, isn't terribly important. The idea is just that we have some mechanism that we can do inductions over formulae. So 3.3 here is, again, doing things that you may even have seen in foundations in proof in the first year, but I think also that Charles has talked about and said. What have we got in here in this first one? We've got the natural number structure. We've got 2 constants in there, 0 and 1. Of course, plus and times, the usual thing. So, and formally, I've written plus in its kind of official version, right? Whereas, of course, normally we would write plus v1, v2 as just v1 plus v2. Okay. And here I've got v1 plus v1 plus 1. So what does all this mean? It says every number is either even or odd. You pick a number, so there is v0 for every number. No, it doesn't quite say that, does it? That's probably what it was meant to say. It's kind of trivial. It says for every number, there is a v0 that's twice that number. Or v0 is twice that number plus 1. Okay, it's true. Given any number, I can always double it, or I can double it and add 1. I think it was meant to say, it was meant to switch around v0 and v1. And it was supposed to say, for every v0, there is a v1. Oh, hang on. yeah, for every V0, there is a V1. So that V0 is twice that V1, or it's twice it plus 1. So this would be saying every number is even or odd if I switched around V0 and V1 here, which might have made a more sensible question. But either way, it would have been true. So then you're supposed to interpret this. And again, it's just exercise in reading these formulae. So this says, pick any two numbers, their product is 0, then one of them is 0. So that's true, right, in the natural numbers. And this one looks like it's true as well. There is a number whose square is 1. Well, it's 1. Okay, so those are kind of straightforward here. And what you have to do for these exercises is go back and look at the definitions of free variable and just apply them, right? And 5 and 6 are slightly more substantial because you have to work out, you have to puzzle out which ones are substitutable and then to actually do the substitutions. Okay, so practice, I mean, this takes a little more thought, I think, down here, 5 and 6. Okay, is there any other help I can give at the moment? Okay, right, well, let's call it a day then, in that case, if there are no more questions. And I'll send out an email today, which I'm inclined to say will be, this is the homework, 3, 4, 5, and 6 here.